Very good evening, good morning, good day. After a break, which of course was due to all of you know the reasons, we have a fourth inaugural lecture by Professor Lalith Rajapakse.
Good evening to you all. May I remove the mask with your permission? Sorry about that. Dear Vice Chancellor, Deputy Vice Chancellor, Dean, Faculty of Engineering, Dean, Faculty of Graduate Studies, Professor Mrs. Jayasinghe, Head, Department of Civil Engineering, all other deans, heads, senior professors and professors, all distinguished invitees who have joined the event physically and via Zoom, dear colleagues and my dear students. Today I feel very honored and privileged to address this distinguished gathering as a part of the inaugural lecture series organized by the Faculty of Graduate Studies. I have selected a slightly odd topic. I remember when introducing the inaugural lecture series, one of our eminent professors, Emeritus Professor Priyandas, mentioned that once the great scientist Isaac Newton selected the topic of colors. I know I am nowhere close to any of those, but I have also selected a topic related to colors. Is the water blue, green or colorless? I am going to talk about my career journey and academic achievements in water research, basically the research and applications in surface water, groundwater and climate change arenas. Before moving there, I need to mention about several individuals to whom I am actually indebted for what I am today. I am a civil engineer who became an academic, and there is an interesting story behind that. I grew up in a totally academic environment because both my parents were school teachers or principals. But that is not the important part of it. Since they were school teachers, they organized field visits to their students during the school holidays. And they sometimes joined field visits with their colleagues. So as a kid, we followed them. And I have visited all Mahavalley multipurpose project scheme sites while they were under construction. And I have even crawled through some of the underground tunnels as access with protective gear was not that restricted at that time. Somehow that experience as a kid inspired a liking in me towards civil engineering, to learn how to design these big structures and how to construct and manage those big things, and it became a dream in my life. Further, my father believed that the actual sense of civil engineering is embedded only in civil engineering. The actual sense of engineering is embedded only in civil engineering. Actually, they never forced us, but I had felt about his preference. I was born in the rural village named Mabodala in Gampaha district, a place which has still not lost its serene village setup even now. And I started my primary education also at the village school. I moved to Minawanggoda Nalanda Central College when I was at grade 2 and moved to Ananda College from grade 6 onwards. By the time I did my O-levels, I had already decided I wanted to be a civil engineer. So then I selected mathematics stream, and that is how I ended up at Moratuwa. So I greatly acknowledge all my teachers and lecturers who taught us and inspired us to become part of the University of Moratuwa and what we are today. Last but not the least, I should appreciate my family, my wife Ganga and my loving daughter Vidara, and my brothers and sisters for all the support and freedom given to me to attend all my research, administrative and project duties and all other work undisturbed. And I use this opportunity to express my special thanks to the Faculty of Graduate Studies who has given me this opportunity to present my research achievements to you all. And I express my sincere thanks to all the staff of the Faculty of Graduate Studies, Department of Civil Engineering too. With this, I will move on to my topic. Is the water blue, green or colorless? But I am not going to give you a definite answer at this moment. I will first talk about my career journey and the achievements in water research, focusing on applications and other research experience. The presentation content I will skip for the time being. And Professor Jayasinghe introduced me, my academic and professional career. So I think I can skip that, but I will briefly talk about that slightly later. Before joining University of Moratuwa as an academic, I had some early academic career or research history. So as Professor Jayasinghe happened to mention, somehow my undergraduate research project was related to structural engineering. So that was to study the buckling of slender files and the resistance from soil media. And then after my graduation, I moved to Japan for my master's thesis. That is where I started learning about groundwater hydraulics. And then after completing my master's, I wanted to gain some field experience. That is how I ended up joining National University of Singapore, and after that also the industry. So after gaining some industrial experience, so while working for this land reclamation project, I did a very valuable investment in my life. I learned VBA macro-based program modules, how to do programming using Excel. So Excel has an embedded Visual Basic application using which we can automate most of the tasks that we can do using Excel, Word and other Microsoft-based software. And this Visual Basic macro has been useful for me throughout my research and academic career life thereafter. And I still believe that learning macro and programming was an investment which I did not realize at that moment. So this has been very useful for my research work as well. So this experience was in 2002. Later I moved to Japan again in 2002 for my PhD study. So this PhD focused on a new area of research, eco-hydrology and eco-hydraulics. So it is a joint research project study with Saitama University, Japan, and Canberra University and Newcastle University, Australia. So I visited Japan, I visited Australia, I think for about 20 times from Japan, where we visited sampling sites, moving around the Newcastle area over a period of week for sample collection and also data collection. And I had the opportunity to collaborate with world-renowned researchers in limnology, lake ecology, and river restoration related fields. So the study produced 8 master's degrees, 5 PhDs, and 4 undergraduate projects with over 8 index journal and 11 other peer-reviewed publications. So after completing my PhD, I had the opportunity to join the University of Saitama University again as a postdoctoral researcher for another 2 years. After that, I moved to the UNESCO Water Center in Japan. There, I had a very good experience working for a Japanese leading institute, the Public Work Research Institute, which is research and also an administrative body. So there I had a very valuable experience with exposure to various international working groups, UN, UNESCO, Mekong Commission, and IHP, and so on. So this exposure to truly international research and teaching career and collaboration with leading water specialists was a life-changing experience for me. So with this 2 years of experience at the UNESCO Water Center, so my main focus area of research, I started with eco-hydrology. As I mentioned, a relatively new research area at that time. And then I am working on surface water hydrology as well as surface water resources development and management, climate change impacts, floods, droughts, and groundwater related studies, groundwater modeling, flood forecasting, and so on. So why water resources management is so important? Water is a fundamental human need. At least 20 to 50 liters per person of clean, safe water is needed for drinking and other purposes. This is actually the minimum. The water supply guidelines are several folds of this value. And in addition to that, water is complex because it is linked to almost everything in the world. But complexity should not be hindering the understanding. Water is a precondition for human existence and for the sustainability of the planet. In addition to that, out of the 17 Sustainable Development Goals set up in 2015 by the United Nations General Assembly, these SDGs are intended to be achieved by 2030. The Sustainable Development Goal 6, clean water and sanitation, and several others are linked to water. So what is then? Famous Chinese philosopher Lao Tzu, he mentioned that nothing is softer or more flexible than water, yet nothing can resist it. So water management has been a challenge to all since the good old days. So that is why water research is very important with the present context. So what are the global water issues? Is there a global water shortage? According to the present assessment, there is no global water shortage as such. But individual countries and regions need to urgently tackle the critical problems presented by water stress. Then how does water scarcity occur? It is because of the distribution of water in different regions with different quota. So only 3% of the world's water is fresh water, and 2/3 of that is tucked away in frozen glaciers or otherwise unavailable for our use. As a result, some 1.1 billion people worldwide lack access to water. And climate change and bioenergy demands are also expected to amplify an already complex relationship between world development and water demand. So because of this, it is very important for us to assess the present availability of water resources and plan for sustainable future use of water resources available. And the map here shows the predicted freshwater stress in global level in 1995 against 2025. And if we move further, water stress by country by 2040. Actually, the situation is getting even worse. Some of the areas in the Indian continent which were expected to be water scarce by 2030 are showing signs of water stress already. So it is not only because of climate change but also due to various other anthropogenic activities. So the climate change is actually worsening the situation when it comes to water resources management. So what are the water related issues in Sri Lanka then? So issues and where we stand based on the records of disasters of the recent decade, the most frequent natural disaster in Sri Lanka is flood, followed by strong wind, landslide and cyclone, all related to water somehow. And what is the impact of floods and droughts on the economy as well as on the population? So in Sri Lanka, we know that there is a spatial and temporal variation of rainfall. We have dry zone and wet zone, and in addition to that, Jala and Maha seasons with distinct rainfall distribution patterns. And increased climate variability as influenced by climate change impact causes more frequent floods and extended droughts in all major basins in the recent decades. So losses due to 2016 floods were estimated at US $572 million, and the losses in Kalani Basin alone was amounted to $153 million US. It is equivalent of 23 billion Sri Lankan rupees. So we can see the extent of damage caused by a single flood event. So in addition to that, the temporal variation of rainfall. We can see in these maps the reservoir storage deficit in 2016 and 2017. So reservoirs are only 20 to 30% full, but no rain. So the rank of our country according to several water issues, we have considered water scarcity and flooding, water quality. So in comparison to India, maybe we are in a slightly better position, But when we compare our ranks with United Kingdom, Bhutan and Australia, we can see we are far behind. So there is an issue and we need to find solutions. That is why water research is very important at this moment. So I will first explain my research involvements related to eco-hydrology and eco-hydraulics. As I mentioned before, eco-hydrology is a relatively new research field when I started my PhD studies. So it is a cross-disciplinary field that emerged in the early 2000s as a result of recognition of the need to better understand complex, multifaceted interactions occurring in terrestrial ecosystems and their connection to the water cycle. So eco-hydraulics is also a similar research field, still growing, and under these we know that hydrology studies basically the abiotic or the natural conditions of the catchment and related factors affecting river basins and stream flows. But under eco-hydrology and eco-hydraulics, we can address biotic as well as abiotic components. So today, with the complexity of issues we find in various basins, this eco-hydrology and eco-hydraulics are playing a major role in finding solutions to those prevailing issues. So, introducing eco-hydrology and eco-hydraulics, the main advantage is the combination of hydrological framework with ecological aspects, that is the target, and then the method. We can use ecological engineering to solve basin-wide issues we are experiencing today. So, if we look at this picture, we can see we are addressing several scales. The rainwater is received by the canopy structure, which is a micro level scale, and then it can fall onto the ground and become a part of the hydrologic cycle. Part of the rainwater becomes overland flow and then infiltrates into ground layer to become groundwater. So all these combinations, and in addition to associated littoral as well as floodplain functions, can be incorporated under eco-hydrology and eco-hydraulics related studies. So we conducted several studies both in Japan and Australia. So in some of the studies we did direct sampling, but in some other cases we had to depend on secondary data, because normally for hydrological studies we have definite data monitoring procedures. But as eco-hydrology, eco-hydraulics was a relatively new field, most of the research institutes did not have an adequate database. So we had to carry out our own sampling, visiting the sampling sites on a regular basis. So this particular study, published in a Q2 journal, River Research and Applications, it focused on the sedge species, and sedges are actually a large type of grass. They can play a major role in floodplains and littoral aquatic habitats. They are affected by flood waves or seasonal flood behavior of different magnitudes in rivers and streams. River hydrology and flow patterns are studied in relation to disturbances to sedges by river spades, and what is most important is these sedge species and their communities can also affect the morphology of the streams and rivers. So these studies provided better insight into flood wave, sedge, sandbar interaction, paving ways for further modeling studies to use nature-based concepts for river restoration, lake restoration related projects. There was another similar study that is also published in River Research and Applications, Q2 journal, and there we focused on various other aspects associated with floodplain management. So in this case, we studied how these sedge species can retain fine sediments, and they can prevent washout of fines, the erosion control due to seasonal flood waves of different magnitudes, and the river hydrology and flow patterns were studied in relation to effects of fine sediment retention and influence of annual chute collapse during river flood waves, and the findings were again used for remodeling these river systems. And another study in similar basin, we studied the wet-dry cycles of emergent aquatic macrophytes and their growth and how the colonization is affected by flood waves, as well as how they can behave as, we call them as ecological engineers to change the river habitat. So the plant species can not only be a part of the floodplain, they can influence the floodplain by forming communities. So these characteristics of different sedge species can be effectively used in river restoration as well as lake restoration related projects. So in addition to the eco-hydrology and eco-hydraulics related projects in Japan, we conducted several studies in Australia. So I will highlight some of the research findings. Okay, right. So according to the series of studies conducted in Australia, we carried out several studies in Lake Myall as well as several selected wetlands in Canberra and in Albury. So the basic findings were useful in preparing database for furthering the research studies, and in addition to that, we continued the same study so that we can develop several ecological models to simulate floodplain and river functions. So these 3 papers were published in Q2 journals and also in Q1 journals. The growth dynamics of various sedge studies, sedge species, as well as the lake restoration related studies in Lake Myall. This Lake Myall is unique because it is located in an upstream part of a basin. So the inputs or the nutrient loading to the lake is very limited. The Australian authorities are very concerned about lake ecology, but during the dry season there had been algal blooms. So they wanted us to study what is causing these unexpected algal blooms. The reason is, since the lake is located in an upstream part of the basin, the nutrient loading is very limited, but there is a very high content of nitrogen and phosphorus in lake water. So we did regular sampling, and we noted that during the dry season there is a huge increase in the nitrogen phosphorus concentrations in the lake water. So during the lake sediment investigation, we noted that there is a very thick layer of, they call it gicha. It is actually a partially decomposed layer of dead material, and they contain huge amounts of nitrogen phosphorus. With the temperature change during the dry season, part of this nitrogen phosphorus is released to the lake water. So they cause nutrient overloading to the lake ecosystem and ending up in algal blooms. So with the climate change, these kind of impacts can become even severe, and the water availability as well as water quality is a major concern when we talk about water resources management. So after completing my PhD study and also the postdoctoral research tenure, I moved to the UNESCO Water Center in Japan. So there we studied surface water hydrology and surface water resources development and management related research topics. So the Public Works Research Institute, where the UNESCO Water Center was hosted, they had initially developed a hydrological model called WEP, that is Water Energy Process Model. But they wanted to use this model for simulating river ecology and lake ecology. So that is where my input was needed. So here the issue was actually, now we are very much discussing about chemical fertilizer usage as well as the excess fertilizer amounts. A similar phenomenon had occurred in Japan during the industrial era. The water quality in most of the rivers and the lakes had degraded significantly, but later, once they realized the issue, they imposed stringent control measures. So they controlled all disposal to the rivers streams, and they managed to prohibit all point source loading to natural water bodies. But you can see towards the end of 1990s, the phosphorus and nitrogen concentrations in the lakes did not go down as expected. So their initial understanding was, when the point loads were adequately addressed, there should be a significant improvement in river and lake water quality, but that did not happen. So then they realized that there is an issue, so they wanted to study it in detail. So the task was given to the Public Works Research Institute. There initially they developed a hydrological model, but our purpose was to use this model for river and lake ecology management. So we need to introduce the nitrogen and phosphorus components on top of this hydrological model. So we had to clearly understand the nitrogen phosphorus pollution traits and why suppression is important. So normally fertilizers are added to various parts of the farmland. Sometimes they may be paddy lands, or sometimes household areas where they have home crops. So all these areas accumulate the excess nutrients during the cultivation season, and when rainfall occurs, part of that accumulated nutrients gets washed away and they end up in rivers, streams and lakes. So in order to study this complicated process, we needed a very detailed modeling exercise. So that is how the demand or the need for this nitrogen phosphorus modeling was recognized, and in this case we combined the existing hydrological model with nitrogen phosphorus simulation modules so that we can simulate the excess nutrient loading and unloading processes, as well as how do they affect the river ecology and lake ecology in the long term. So watershed nitrogen phosphorus export is largely controlled by coincidence of high nitrogen phosphorus source areas and the runoff generation, because normally when the phosphorus or nitrogen is accumulated on the ground, we need an erosive source. Normally the runoff water can bring huge loads of nitrogen and phosphorus to rivers and lakes during the rainy season. So when we manage nitrogen phosphorus and when we want to introduce best management practices, we need to study both low flow characteristics and high flow characteristics of river water. The importance is, during most of the period of the year, the river flows with mean flow rates or low flow values. But during the rainy season, the discharge can increase suddenly and the overland flow process can dilute or dissolve huge amounts of accumulated nitrogen phosphorus on the ground and convey them to rivers and streams, at the end ending up in the lake in the downstream. So we studied the high flow, low flow characteristics in the basin, and we try to introduce best management practices for watershed management. So the objective of the study was to identifying the nitrogen phosphorus pathways, and then treatments and best management practices, how to develop them, how to implement them, and to develop the process-based modeling tool. We wanted to improve the existing hydrological model, combining nitrogen phosphorus dynamics into the hydrologic model. So we selected a sample study site that was Yatta River Basin in Ibaraki Prefecture. So that is a basin with 166 kilometer square area, and we carried out a regular sampling session, detailed sampling for river water and also for lake water quality. And the basin history indicated that the downstream Ushiku Lake was listed as the third most polluted lake in the Japan in 1999. So subsequently, a huge degradation in groundwater quality was also observed in the basin. So that is one of the reasons why this particular basin was selected for pilot studies. So this web model, or the water energy transfer process model, had been tested at several locations earlier. So we were confident about the hydrologic modeling component, but the nitrogen dynamic part was new. So we used the data collected from the pilot basin to calibrate and validate the model. In the water energy transfer process model, the hydrological processes were simulated in detail: evapotranspiration, infiltration and runoff, and the subsurface flows, and channel routing and river flows were addressed by using kinematic wave method, and also additional biogeochemical modules were incorporated for nitrogen phosphorus dynamic simulation. So the basin-wide data collection procedure continued for almost 1.5 years, and then we wanted to test our model using collected data set. So these are the basic governing equations. I will not try to elaborate them here. But what is interesting is when we incorporate the material balance part to the model, the hydrologic model component also indicated a huge improvement in simulation results. Normally, a hydrologic model works based on water balance concept. That is good enough for event-based modeling, for modeling one single event or a short period of time. But when it comes to longer duration modeling, the water balance alone cannot maintain the required accuracy. But when we introduce the material balance and the energy balance on top of that, we can use the energy balance as well as mass balance, material balance concept to fine-tune water balance parameters. So there was an additional advantage of incorporating material balance components to this hydrologic model. So with this exercise, we verified that the model is capable of simulating not only the hydrological processes but the nitrogen phosphorus dynamics as well. And luckily in Japan, we have all the records of chemical fertilizer usage for a particular region as well as for a particular season recorded at the government authorities. So we collected these data and we tested them using our model. And what we noted was we tried several modeling scenarios. If we reduce the nitrogen and phosphorus input by 25%, if we reduce nitrogen phosphorus input by 50%, what will be the impact on the river water quality? So the results were quite promising, and we found that the long-term deterioration of water quality in the downstream lake Ushiku was mainly due to the non-point source pollution, not due to the point source pollution. Actually, the point source pollution had been well addressed, but there was no particular method for assessing this non-point source pollution component, and the developed model could be applied for that task very successfully. And the results indicated that there is a definite imbalance in the fertilizer input and plant uptake. The resultant amount is accumulating on the ground. And towards the end of the period, the rainfall season coincides with the harvesting time, towards the end of the harvesting time. Then there is a huge accumulation of excess nutrients on the ground as well as in the paddy field areas. We use this excess nitrogen phosphorus as input data to the improved nitrogen phosphorus simulation model. So using a grid resolution of about 100 meters square, we could easily identify what are the source areas of excess nutrients and what are the deposition or the most affected areas in the downstream due to this excess nutrient washout. So these are the results of the hydrologic model component, and this is how the verification and the validation was done using observed data as well as simulated data, both for the temporal and spatial variation of rainfall and river water conditions. And the most important finding was we could easily identify the reasons behind the water quality deterioration in some of the major groundwater well locations in the downstream area. Because with time, the surface runoff is very fast, that can remove a huge amount of nitrogen and phosphorus during the major rainfall events, but the infiltration causes a slow accumulation of excess nitrogen phosphorus in the underground layers. They cause deterioration in the groundwater layers in the long run. So we can see the spatial distribution of nitrogen phosphorus amounts, and we plan for the management applications implementation of best management practices focusing on the model findings. So after the end of my tenure at UNESCO Water Center in Japan, I decided to come back to Sri Lanka. I am thankful to some of my colleagues who helped me in making those important decisions. Because when I was in Singapore, I didn't want to leave that very enjoyable, lucrative job. I liked field experience as a civil engineer, but some of my colleagues who were there forced me to go for higher studies. And same thing happened when I was in Japan also. At the end of a 3-year term, before renewing the contract, I had some commitments, so I decided that is the time to come back to Sri Lanka. That is how I ended up at University of Moratuwa. And we used the same model in Sri Lanka. We selected Malwatuoya Basin and we applied the model with available limited data. The model results were quite interesting. Even with the limited data availability, we could identify that there is an excess nutrient loading in major parts of the basin. So basically the paddy areas as well as multi-crop areas, they have reasonably high excess nutrient amounts accumulated as a result of fertilizer usage. And the final result is during the rainy season, they get washed out and they end up in streams, rivers and the lakes. You can see some of the model results as well as model calibration validation details. Due to time restriction, I may not go into details. Here also we simulated several scenarios. If we reduce the fertilizer usage by 25%, by 50%, what will be the increase in stream and river water quality and also the reservoir water quality? There was a significant difference in the different scenarios, and that indicates that the natural systems can well respond to the changes in our inputs to the system. So that is why basin management is a very important tool in water resources management. So in addition to the nitrogen phosphorus dynamics, we could simulate the groundwater pattern in the basin. But unfortunately, we have only limited data set when it comes to groundwater resources. So we plan to extend this study when we are able to collect a reasonable data set for groundwater measurements. And you can see the nitrogen phosphorus loading and what is the impact in the basin. The next topic I want to cover is climate change impacts. We know it is already apparent, it is not a pending issue. We can feel climate change impact, and the major basins in Sri Lanka are affected in various ways. They have floods during the wet season, and due to the high climatic variability, we face extended droughts causing huge damage to agriculture and other daily livelihood activities. So in this study, we use climate prediction data. Normally, climate prediction data is available for large regions. They are not available at basin scale. So we used available general circulation models and also the regional circulation models to downscale climate data and apply these data to Kalani River Basin, and then to determine the changes in the river water discharges, what will happen in 2050, what will happen in 2100. So this information will be needed for basin water management planning as well as for other development activities. And this research was also published in Paddy and Water Environment, that is an international index journal. And in addition to that, one of our postgraduate students who completed his master's study here and returned to his country, Pakistan, he initiated a study in Hakra Basin. It is a huge basin compared to our own basins here. The canal network amount to colossal 30,000 kilometer length, and there are water distribution issues. So we used modeling exercises to identify the bottlenecks, as well as we managed to give recommendations to improve water distribution efficiency. And this research was published in irrigation. Sorry, I can't see the screen clearly. It's small fonts, so that is also published in an international journal. And when it comes to Sri Lankan water management history, we are very famous for managing cascade systems. Conference in 2017, we were planning to have another in the year of 2020, but we are postponing it due to the present condition. So I think we will be able to have it very soon. In addition to the research, we are promoting various training programs there, and we have an outdoor research facility for irrigation, urban drainage, soil moisture studies. And in addition, we participate in various webinars, workshops, sharing our research experience with agencies, individuals, and organizations. So some of the research were awarded with, recognized with the award of certificates, and of course the credit should go to the students involved as well. And in addition to that, I have listed some of my project experience, but I will not go through them in detail. I will just highlight some of them, and I will move on to the final part of the presentation. This is one example related to the port city development. There we had an issue with increasing groundwater layers due to the planned reclamation. So we used a modeling exercise. We collected initial data sets, and we carried out a comprehensive 2D, 3D modeling exercise to identify whether there can be a significant increase in the groundwater levels due to the reclamation activity. We found that when an additional mass of soil is added, a reclamation is carried out, there can be an increase in the groundwater level. So that cannot be avoided. But what is important is how to plan for mitigatory measures and how to identify this exact amount of raise or the increase in the groundwater layer. So there had been some initial modeling exercises, but they had produced very significant inundation due to increased groundwater heights. But during our modeling exercise, we found that very high groundwater level increase can be predicted if we do not use our modeling properly. So in our case, we used 2D groundwater model, and using the rainfall input as well as surface water bodies, surface runoff flows, we identified what could be the impact to the groundwater table. And we found that if we set our initial conditions differently, there can be false predictions. So here what happens is the initial modeling has been conducted assuming that the land reclamation or the reclaimed land has an indefinite width. So the actual condition is it is open to the ocean by other sides as well. So the groundwater does not have to follow the longest path. It can spread over and get released to the ocean. So when we introduced these actual conditions, we noted that the impact can be minimized to a greater extent. So in addition, we introduced a monitoring procedure to ensure that there will be no significant impacts due to the land reclamation associated with Port City. And then the next example is for constructing a tunnel underground of the goal face green. The government is planning to extend the existing marine drive across the goal face drive to reach the newly reclaimed Port City. But there is a condition: the goal face green cannot be blocked due to a past decision taken by the authorities. So the only option available is to go underground. But when you construct an underground canal across the goal face greens, there will be a significant blockage to the groundwater flows. So the contractor wanted us to study how to minimize this impact. So again, we used an extension of the Port City model to simulate the groundwater conditions here. And we noted that, of course, there can be an influence because the free groundwater flows will be blocked by the tunnel as well as the apron walls constructed to facilitate the construction. So we carried out further modeling exercises to identify what are the possible mitigatory measures. So at the end, we realized that, of course, there will be a significant increase in the groundwater level if we implement the proposed construction procedures as it is. But there can be mitigatory measures. We can provide through flow across the apron walls, as well as we can keep part of the tunnel open. So there will be a connected ground unit which will allow groundwater to release to the ocean. So by proposing this particular method, we managed to recommend that the proposed solution can be implemented, but with the suggested mitigatory measures. So with this, I think I will move on to the closing part. There are several other examples, but I think I am running short of time. But I think I will not be allowed to close the session because I raised an issue at the beginning. So that is about the color of water, right? So I will directly go there, skipping this final project example. That is about transfer site in Kalaniya for Aruwakkalu waste management site. But I will skip it and then go to the closing site. So what is the color of water? That is the question I raised at the very beginning. Is it blue, green, or sometimes red, or is it really colorless? Actually, the answer is the water is not colorless. Even the pure water can have a very small tint of blue or hue due to the absorption of light rays towards the red zone of the light radiation. But here what I am referring to is not the physical color of water. According to the water science nomenclature, we have a classification. We call the surface and groundwater that is stored in rivers, lakes, aquifers and dams, and that can be extracted for our day-to-day use as blue water. Then the part that gets infiltrated into the soil layer, that can be absorbed by plant roots, and then they can be released to the environment through evapotranspiration. That part is called green water. And then we have the gray water, which is household wastewater, and also irrigation return flows are also sometimes called as gray water. So then the answer to the initial question I raised, whether the water is green, blue or colorless, yes, physically it can be either of these, but I have been referring to the water science nomenclature. So the research I produced or I explained referring to surface water flows, groundwater flows, they fall under blue water. Thank you very much. And I extend my sincere thanks to the Faculty of Graduate Studies for providing me with this opportunity. Thank you very much.